Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So, this week we will cover design principles. So, as we have been discussing, the products today, this is what they look like. They are very efficient, elegant and very affordable at the same time. They are smaller in size, but full of features. The quality, reliability and performance, definitely we do not want to compromise, and most of the time we get in these products today. And the machines today, they look very unconventional, very different, look very complex at the same time. But what we also realize that they are very precise and very fast moving, because again we do not want to compromise with the yield, and that is how we make it affordable. The products we make, the parts we make, they are still affordable within the price. At the same time, the alignment, adjustment, they are in place so that we get the right quality. And many times what we also realize that these machines are used to create features in micron or even nanometer level, so that we can make things in a very small footprint. They take very small space in the overall device or machine, and that is how we can get many features in one machine or in one product. So, we will look at some of the machines and how they work in the next video. So, here we talk about design principles, and what we want to learn or emphasize is how to make these machines, how to make these products or these machines, so that we get the things at the right time and we get it at an affordable price. So, many times for mechanical engineers and mostly for the beginners, for instance, our undergraduate students, after completing their bachelor's, they do not know where to start. So, when we have to design some products or machines, right from the specifications, how to proceed and what are the elements we have to consider. So, many times what we realize that these design principles or the rules, or what we can also call it elements of mechanical design, they come through experience. One who is working at the shop floor with the machines, designing machines or products for different application, they realize that what are the things which works most of the time and what are the things which does not work. So, it comes through experience after working for 10-20 years. They have the know-how, sometimes it belongs to the firms, to the companies where we are working, and the intuition of the expert designers. But the problem is how long one can wait. The best way is to learn, is to make mistakes and learn, but then it will take a lot of time, and then a lot of mistakes means a lot of money, and it's going to be a costly affair. So, definitely some we learn from our mistakes, but we learn from others' mistakes, and we know what are the principles, what are the rules, what are the thumb rules one has to use. So, I think we already talked about table with the 3 leg and 4 legs, and we know the difference. 3-legged table very common, and usually they are stable, they don't rock. But we also see tables with 4 and more legs. But if we are using such designs, we have to be aware of the constraints, what kind of problems we can face, and how to eliminate that. The very simple examples, I think with our experience we also learn that in this case the symmetry, like if one has to carry some weight or a bucket of water, we do realize that it's always better to carry 2 buckets than one. And suppose carrying a load working on the fields, but we realize that if it's loaded on both sides, it's much easier to carry, and that way we can carry more loads. But if we have to carry just one load, many times it's difficult. Another example is just a tripod, and we use it very often if we do some kind of cooking, or if we have to make some makeshift kind of frame for weighing machines, that we always see that they are 3 legs, not 4 legs. So, the idea is whether we can use these principles, what we learned or what our experienced designers, engineers, they have built in the machines. So, for instance, this machines conventional lathe what we have, many times we see this kind of designs, V and flat. So, it's supported on V and flat here, and what we can see here is there is one V here and one flat is supported here. At the same time again here we see a V and flat. So, I think what is the basis? Why we need to have V and flat? I think these are the things we need to understand, and whenever we design things for precision or for even normal applications, we have to take care of these things. So, in the current systems, when we are building systems for automations or robotic applications, those V and flats are replaced now with these kind of linear guides. But are you aware of V and flat, and if we are replacing with this kind of linear guides, what kind of problems will be there, what kind of compromises we are making, and if we are going to use these kind of linear guides for precision applications, how we are going to eliminate if there is any kind of over constraint. So, these are something we will be talking about. If we talk about bridge design or the power transmission towers, very nice design and very elegant, what we can say, and what we can also refer to whether these kind of structures, whether we are using to even build the machines, and or how it can be used to build the machines which are not heavy, which are stiff, but not very bulky. So, some concept, I think in day to day application many times we see that these kind of scaffoldings are used, and these are not designed by engineers or experienced I would say engineers, but yes, definitely designed by experienced workers who are using them uh, for whitewashing, for carry out any kind of work at heights. And what we realize that the design principles are embedded. If we compare a bridge structure with these scaffoldings, we can see the elements, and that is what we will be talking about in this course. On the other hand, if we see these big structures, big machine frames, I think what we need to understand is whether these principles, basic principles, whether it has been used to design these frames, so that we can eliminate any kind of instability there, and whether we can make use of these design principles to even create structures for our machine frames. If we go further, what we realize in today's time, we are using a lot of aluminum extruded channels to build systems or machine frames quickly for automation system, for robotic applications. And many times we may realize that these things are missing the basic design principles to get rigidity, enough rigidity. I think they are missing. And so, if we are using this kind of aluminum channels, whether we are aware of or whether we can use these principles to make this structure stiff enough to take the load and give the right performance. So, for instance, this is from Barcelona Olympic Stadium tower, and if you can see, it's a very unique design. And suppose if we have to design this kind of structures and the support should be minimal, then what is the approach? So, if we understand these principles, I think it's very easy, and even it's important for us to appreciate how it has been designed and placed there. So that one can see it and through, and then one can really appreciate how it's supported. So, we can also see tubular constructions for Formula 1 cars. So, similar concepts here. Yeah, one can say here the extra load coming on these tubes is also torsional load. In most of the trusses, what we realize that the kind of loading is only longitudinal. So, it's either in tension or in compression. Here it will be in torsion as well, and rarely there will be bending loads. So, if we try to summarize and try to list down what are the rules, what are the design principles, if one is looking at configuration of any machine or any products. So, this has been listed. So, many people have worked earlier, and there are many good books. So, this has been highlighted. So, that's what we can say, elementary rules of mechanical design, which will be equally applicable when we are designing for precision. So, we first go through these elementary rules or design rules one by one and try to understand why they are there, and then we will move towards the other design principles which are required for precision. So, first what we are saying is, so create designs that are explicitly simple. So, it has to be simple. We always tend to design things which look complex, right? So when we render it, we can see different reflections and it looks very nice. But on the contrary, what we are asking is design something which is very simple. The second rule is keep the functions of our design independent. So we want to separate the functions. So one element, one component should be used to carry out one function only. We'll see through one example that why is important. Next is what we will be emphasizing all the time throughout the course, that use exact constraint design. So we'll talk about what is exact constraint design and what it means. Plan the load paths. So there will be some loads, some forces coming, dynamic loads, or because of the tooling, because of any operation we are performing, there will be loads coming to each other. So how we plan it, how we should plan it, we should know exactly. Triangulate parts and the structure to make them stiffer. So that's what we see in the bridge design. And when we want to design machines for precision, we really want to have very high stiffness for the frames or the machine bases. So how to design so that we can get a very good rigidity, very good stiffness. So if we are looking for stiffness, then the idea is to avoid bending stress. So but we also realize that it's very important that if we want to have a stiffer structure, most of the loading should be either in tension or compression. But if we need compliance, if the stiffness is low, so when we will be talking about compliant mechanisms or flexures, then we will be talking about bending and torsional loads. But if we are looking for stiffer structures, then we try to avoid bending stresses. Next is improve design with self-help, and usually what I call it mechanical intelligence. So it's not artificial intelligence, but it's a mechanical intelligence. Though it's an inanimate object, but the way we design things, a designer conceptualize the thing, it's likely that it will have intelligence embedded into the design itself. So we'll look into some examples. And the last is manage friction in mechanism, because friction gives a lot of uncertainty, a lot of randomness in the results, and that's why many times we try to manage, try to eliminate friction, and this is again we will be talking about these things in the later slides. So coming to design principle 1 or rule 1, where we are saying create designs that are explicitly simple, keep complexity intrinsic. What does it mean? So we try to emphasize again, we call it KIS, case, keep it simple, or say simplify, simplify, simplify. So whenever we discuss, whenever we have a design review, we will always hear from your seniors, simplify the design. And if there is any kind of complexity, it has to be intrinsic, it has to be embedded, it should not. So if we design something, we always start with the simple blocks. We don't want to introduce any kind of complexity, and later we realize that if there is any complexity, that will lead to cost, and that is the reason we also want to avoid complexity in the design. Simplicity also important because if it's a simple to use, then the abuse of the product of the system or any mishandling can be avoided easily. So, like the phones these days we see that even a child can play with the phones very easily because it's so intuitive. So, one of the thing, if we talk about the simplicity, what we can easily bring into our designs by just using the symmetry. So, if we see these examples, so this is a symmetric design, and what we realize that if we have this key, the double sided keys, so it can be easily inserted in the keyhole and can be used, either way it can work. On the other hand, if we use the asymmetric one, yeah, it has to be precise, and means we are using it in the night, and if there is by chance if there is no light, then sometimes it's very difficult. So, what we also see that symmetric items, they are simpler to use and assemble, right. For functioning is it's very good, it's easy to use, but it might be complicated to produce because there might be operations required to make it symmetric. So, when we say the complexity, this is what we mean. Any kind of complexity in manufacturing, those things should be hidden, and to the user it should be simple. So, how you can implement in our designs? So, when we are designing products, and when we have to design any kind of component, the best way is to first use the standard components, because they are made using the standards. So, yes, we follow the guidelines, and then we simply select those components based on our loading conditions, based on our requirements, and use it. So that it's not, we don't have to design everything, we don't have to calculate everything, we don't have to manufacture everything. If that is not possible, then we specify component by standards, using standards. So, very good example of these things are like screw threads. So, we do not always make screw threads, we just define or state whether it is what kind of screw threads are there. Other is bearings. So, we only select bearings based on our requirement, based on the life, the dynamic loading, the loading conditions what we have. But we most of the time select bearings, and bearings are made by the manufacturers using standards. They have to follow each and every standards, so that they should not fail. So, it is a very complicated component. If we just look at a bearing, there are so many parts involved, but to designer is just one component. And so, it is simple to use, but at the same time the complexity is hidden, is intrinsic, and yes, it is definitely to the manufacturer, it is very complex, but again they use this principle to provide the ratings what is specified in the standards. Coming to the next design principle, rule 2, keep the functions of a design independent from each other. So, we try to decouple. What does it mean? So, what happens when during the concept development stage? So, if you are involved in the design process, if you are designing product or a machine right from the scratch using the designer specifications, we start with the concept development, and we will try to get try to find different functional requirements. So, what we are saying here is we first try to decompose a device or system into basic functions. So, we get the functional requirement, and as a mechanical designer, the first thing we should do is to keep these functions separate. They should be independent. Very good example here, like we might have seen in many places. So, this kind of tripods we see in the market. So, yes, the camera these days more or less now obsolete, but maybe it has been taken over by the mobile phones. But yeah, this kind of tripods we can see where like we have this ball, and then there is a groove, and then we tighten, and we can do the orientation, we can position the camera. So, if you are looking at the functions, what we want is first want to define the camera positions, and second function is to lock the camera in place. So, I think whenever we deliberate on the requirements, I think very important that we understand what are the functions, what are the different functions we have to achieve, and then only we should be able to eliminate any kind of problem we have. So, in this case, first we want to orient the camera. So, position it and then lock it. So, what happens in this case when we start locking? Locking is done by turning this nut, and as we turn it, it goes down and then starts making contact with this spherical ball. So, there will be there will be contact made by this outer collar when. So, what happens when we are turning? So, it is turning at the same time is also going down, and moment it comes in contact, there will be a fight, and whenever we try to lock it, the position will get disturbed. Of course, it depends on what kind of application we will have, and suppose if it is for just a normal point and shoot camera for nearby objects, it might be okay, few degrees here and there, one may be fine. But suppose if you want to use it to point and shoot some object or a tiger which is maybe 100-meter away or 200-meter away, then that 1 degree, 2 degree kind of disturbance will have a lot of effect, and it can be many times frustrating and annoying. So, this kind of problems many times we have encountered, not only in this case, but may sometimes suppose if we are fixing mirror at home, we will face similar kind of problems. So, how to address this part? So, yes, as we said, so there are two functions, positioning and locking, and there is no functional independence. They are integrated, and we are trying to achieve both. So, of course, the number of part counts is small, but then because there is no functional independence, we will face a lot of issues. So, one of the way to address is like I think very clever design here. So, what we use is a ball and socket head, and then we use slotted collet. So, here we can see the slot, and what we realize that here we are using a little bit of compliance. So, what happens when we are turning it, this nut presses this collet. So, it presses and then this collet will grip the ball. So, what we can say, there might be clearance in the beginning. So, and then we have, so it will get pressed against the ball and then so here there is no direct contact between the nut and the ball, and therefore, when we try to lock it, it just forces the collet inside and then locks the ball in position. So, what we can see is a very good use of compliance here as well, and if the functions are independent, then the locking and positioning can be carried out nicely. But what we also realize in this case, yes, again, if we look at it closely, what we realize that the positioning again requires, the requirement is rotation along 3 axes. So, now we have multi-axis pan head camera mount and functional independence of all 3 rotational locking and positioning functions. So, in this case, what we realize that we want to have all the 3 rotations. So, we want to position one by one and lock it. So, we have this handle design. So, we want to have yaw motion, then we can move it that way. For pitching, we can have this motion, and for similarly for roll, we can have this motion and can achieve it. Now, if we see it closely, what we realize that the arm has 2 things. So, by moving up and down, we can aim, and by just twisting it, we can lock it. So, and this is again, you can see in all the 3, this is very nicely achieved. So, we can also see a use of compliance here. So, combined adjustment and locking. So, in this case, yes, one handle is doing both. So, we have combined adjustment and locking function, and it's mainly to reduce parts count, and one can operate it intuitively. Moving on, the rule number 3, use exact constraint when designing structures and mechanisms. So, never over constrain a design. What does it mean? So, never over constrain a design is, so I think it will be clear with some examples later. So, provide a constraint what is required, but do not overdo. And even in the design, what we realize, if we do that, if we over constrain a design, the parts, the components will start fighting. And in general, what we say, never start a fight, I think it is also true in case of machines. And when we assemble components, it is very important that they should not start fighting. It means the same function, they should not start sharing, otherwise there will be some kind of over constraint, and there will be stresses build up without any useful output. So, I think what we need to also understand is what is exact constraint, and if it is exact constraint, we also call it kinematic design or minimum constraint design. So, what is minimum? So, if when we talk about constraining anything, and if we want to constrain the movement, so what he is saying is, if we rigidly constrain a component at more places than what is needed, then there will be a fight between these components, and we will have over constraint, which is not desired. So, in a way, exact constraint means applying just enough constraints to define a position or motion, no more, no less. So, how to find what is enough, what is just enough, right? I think this is the keyword, or what is the minimum constraint required for any machine or any mechanism to function. So, for instance, if we look at this design, in many cases, particularly when we see carpenters putting two planks together, and if we have to, they have to use this screw, they straight away start, so no drilling, nothing, but directly they try to connect them. So, and many times we see these kind of problems, either there will be gap left, or whenever, or it will turn. So, very difficult to get the exact positioning. Of course, yes, we can use the brute force, we can just stand on top of it and try to do that. So, we make use of the compliance of the board and try to assemble it. But yes, this is not the right approach. So, if we really want to get that connection done, usually we need to have a clearance hole here, and then put the screw, and we can get the connection done. Similar example is, if we have to connect this hub to the shaft, how to connect them. So, if we have this kind of assembly, so suppose, yeah, we have a hole here, and then we are putting a pin to lock. What we realize that it's very difficult to align the two holes together and insert the pin. So, of course, other trade-off is we can have a clearance and find some way. Another way is we first do the assembly and then do the in situ drilling. So, once the assembly, once it is assembled, we drill, make the hole, and then insert the pin. But again, that is not a complete solution, it is a partial solution only, because what happens if it is for maintenance, for serviceability, if you have to remove the parts and try to put them back, it is again going to give a lot of problems. So, over constrained hub and shaft with the pre-drilled holes is very difficult. Even in situ, that is also not going to help. So, what are the other approaches? So, a very good example is 3 bearings on a shaft. So, definitely it is over constrained design, and many times we ask, okay, how many bearings for a shaft. So, yes, if you want to define a line, usually this is what we learn most of the time. Yeah. And again we have rollers here. And the idea of using bearings is to support the shaft, and so a shaft carries many components. So, it provides the rotational axis. So, rotational axis is basically in this case, yes, all the parts mounted on the shaft, they should have the rotate with one axis. But what happens if it's a long shaft and then we try to put too many bearings, for instance 3 bearings, what are the issues? So, I think if we are aware of manufacturing issues, what we realize that yes, very difficult to get a straight shaft, that is one thing. On the other hand, if we try to put the bearings, what we realize that very difficult to align them in one line. There will be a lot of tolerancing here, here, in all the places. So, definitely it is not advisable, because any error there, any crookedness in the shaft, any offset in the middle one, suppose if it is supported on the last 2 bearings. So, it may be okay when we assemble it, but as it starts rotating, any offset will try to just put a lot of constraint on the shaft, on the frame, and will have a lot of issues with the design. This is one example here, again for mounting a shaft with the bearings, and what we realize that if we look at this design, the shaft, and there are 2 bearings here, so left and right. What we realize that if there is load in this direction, yes, the end caps are there, so it's blocked, the movement is blocked by the end cap on the left. But if there is a force along this direction, this side does not provide any kind of support, but it is blocked from this side, from the right side. One can say it is good enough, and since it is a constraint from both sides in the left and right directions, it might be okay. But what we realize that yes, at the time of assembly it might be okay, and many times we call it form closure. So, we need to know exactly what is the length, and if there is any offset. So, of course, we have to use the spacers to get rid of any kind of clearances what we have. So, we can pack it and assemble it nicely. But what we realize that if there is a little force there, extra force, it will come to the bearings and it will dislodge the outer and inner races of the bearings. On the other hand, if there is any kind of thermal expansion or contraction, since it is locked from both ends, if it tries to expand, there is no room to expand. So, again it will apply a lot of load on the inner side, and again this will dislodge the bearing. So, in this design, if the bearings are failing, it is not because bearings are of low quality or a bad bearing, but it is mainly because design is bad and there is no relief provided for that kind of expansion or contraction. Now, go to this design. What we realize that on the left, the bearing what we have here. So, yeah, if there is a load here, of course, is supported from the left side by the end cap, but if there is a loading on this side, there is a wedge here, again this will also provide the support. So, actually the design what we are talking about is so it is very much like this. So, we study all the time, but many times we forget to use it when we are doing the detailed design and trying to achieve a good design. So, what we see here on the left is a lock through the bearing, entire shaft. On the other hand, what we see on the right is a simply supported. It's a flat, so it's a floating end. So, if there is any kind of thermal expansion and contraction, it can simply shift, it can slide easily without putting any kind of loading on the bearings. So, definitely it's a better design and this is not over constrained. So, this is what we mean when we talk about over constraint, and when we talk about adjustment, these are the kind of DOF we are talking about, degree of freedom we are talking about. So, if we have exactly constrained design, we will address a lot of issues what we usually have when we have over constrained design. So, if it's exactly constrained, there will be no binding, there will be no play, it's a repeatable, it will always go to the same location. Since there is no fighting, so there will be no internal stresses because of the assembly. There will be no loose tolerance parts because we do not have to accommodate. So, there is no uncertainty, we know exactly what is going on, and if there is any kind of error, okay, there will be a, if there is any error, the parts will float. So, there will be no loose tolerance parts. The assembly will be easier because we know what are the sequences, how it's getting locked first and then how things will be placed. We do not have to look from both the ends. And of course, since it's a deterministic, the loading we can easily calculate if there is any axial load, where it's going and up to what extent. So, yes, it's robust enough, and robustness to wear and environment we can achieve. So, we will talk more about exact constraint design, and we will take more examples in the next lecture. Thank you.